All right, so our next topic is the topic of convergence. And we
Hocam
will
ekran bizde
paylaşmadık mı?
yok.
Sorry about that. So share screen. Okay, can you see my screen?
Yes.
Perfect then. So our next topic is convergence. So in this topic we will be dealing with series defined in the normed vector spaces. So, and investigate some definitions such as convergence itself, the different sequences, Cauchy sequences, completeness, etc. So let's start with our very first definition. Okay, let VF and that norm definition be a normed vector space. And let Vn, for n is from 1 to infinity, be a sequence of vectors in our vector space. Then this sequence is said to be convergent to a limit, v bar here. So notice that v bar has to be an element of the vector space itself. And as n goes to infinity, we want the norm between Vn and v bar should go to 0 as n goes to infinity. Okay. And as you might also remember, we check those conditions by defining the limiting conditions for the sequences by giving the definition of a given any epsilon greater than 0, there exists a n, which is actually a function of the epsilon, such that for all the small n values which are greater than capital N implies that the difference, the distance between Vn and the limiting value V bar is less than or equal to epsilon. So if we try to picturize that, so yeah, grab my pen. Sorry. So suppose we have such vectors, okay? So let this be 1, let this be V2, let this be, I don't know, V3. And we continue like this. And let's say we have, making it of this one. Sorry. Okay, I will not push the program. Okay, so suppose this is V1, this is V2, let's say this is V3, and let's say this is V bar, okay? And suppose I pick, let's for example, let this guy be the, I don't know, let's say V, this be the V100, for example, and we continue like this. All right, so what we would like to do is that, so we will define a ball of radius epsilon. So pick another pen. So around V bar, for example, that might be one ball with a radius epsilon 1. Okay, let's say like the ball radius epsilon 1, or what is that? And here is another ball with radius epsilon 2. Okay, that is a ball with radius epsilon 2. So what we like to show is that, okay, so if you give me an epsilon value, I can give you a number n. So for all the integers greater than that n value, the distance between the vector in our series and the limiting vector is less than that epsilon value. So that's pretty much the idea. Do you have any questions? Okay, so And our next definition is that which comes with the convergence is the divergence, and a sequence that is not convergence is simply called a divergent sequence. So let us see one example to understand the concept better. So consider the vector space of the real line, and the norm of these numbers are defined as the absolute value of these numbers. And we have the sequence Vn is 1 over 2 to the power n, and n is changing from 1 to infinity. Okay. So if we plot the real line over there, that's not the way I want to plot. Okay. So suppose this is the real line, and suppose this is 0. So where is the first element of that series? So when n is equal to 1, v1 is over here, right? So let's say this is 1 over 2 as v1. And v2 is at 1 over 4. So there, v2. And v3 is somewhere over there. Wait, and that is v3. Okay, so in order to show that that sequence is convergent to 0, okay, so we would like to, if I give you an epsilon interval around 0, you should be able to tell me a number n for all the integers greater than n that vector falls into that epsilon radius. So let's also plot this epsilon radius over here. So given an epsilon, something like this. Okay, so this distance is epsilon, and that distance is also epsilon. So for any given epsilon, I should define the n value, right? For example, so if epsilon is given as 1 over 8, then what should be n? So for all small n values greater than n is equal to 3, that the vectors will fall within the epsilon neighborhood of that 0 vector over there, right? So if you tell me as epsilon equals to 1 over 16, then I can say n is equal to 4. And if you give me any number, I can find an n value greater than that. I can further write that as in a mathematical expression, right? So the norm of Vn minus V bar, we just said this was equal to 0, okay? If we are showing that thing is convergent to 0, it simply equals to the absolute value of 1 over 2 to the power n. And we want that thing to be less than or equal to epsilon, right? So that equality is, if I take the logarithm of both sides, so that equality will be satisfied when n is equal to minus log 2 epsilon. And so for any n values greater than this value, the equality will be 1, because for larger the n values, the smaller the left-hand side of this equation will be. Okay, so if I pick n to be equal to ceiling of minus 2 epsilon, I can assure that for all the elements in the sequence which are greater than n will be at least close to within the epsilon neighborhood of the limiting value over here. And so this was a convergent sequence example. So these sequences obviously goes to 0 as n goes to infinity. So let's consider another sequence which won't be the case, which is not convergent. Let's see, divergent. So let this be the real line, and I am considering the sequence minus 1 to the n over there. Okay, so And what I would like to show is that I will define the norm of the vector as the absolute value of that vector. And the question is the sequence convergent to 0? Convergent to 0. Okay, so let's start by plotting the first of the limiting factor, 0 over there, and also placing the elements of the sequence on the real axis. So when n is equal to 1, v1 is equal to minus 1. So this is minus 1, and that is v1. And when n is equal to 2, v2 is equal to plus 1, and this is v2. And v3 will be at minus 1, so v3 will be here, v4 will be there, etc., etc. It will be something like that. Okay, so for given an epsilon, I should be able to find the n value such that the vn minus 0 is less than that epsilon for sure. Okay, and let's start with the epsilon values. Let's say epsilon value is equal to 2. Okay, which means that I should go to the limiting value 0 over here and check the epsilon neighborhood. So this is epsilon 1, and that is again epsilon 1, and I should be able to find the n value for the n value is greater than that n value. This difference between the omega n minus v bar is less than or equal to epsilon. Okay, so, and in that case, if epsilon is equal to 2, given an epsilon is 2, that n value is simply equal to 1, right? So 1 is equal to 1. But if somebody gives me an epsilon value as 1 over 2, then if this series was convergent, I should be able to find the n value for which any integer values of n greater than that capital N, the distance between Vn and V bar should be less than 1 over 2. So let's plot the epsilon 2 over here, neighborhood of the limiting value over there. And for if I'm given epsilon 2 to be equal to 1 over 2, I can't find any n values. Okay, so no n values can be found. So that norm of Vn minus 0 is less than or equal to 1 over 2 for n greater than or equal to n. I can't find such n value. So therefore I can conclude that the sequence is not convergent to 0. First, the sequence is not convergent to 0, or it's not convergent to any number actually, so it is not convergent to any number actually. So this was one definition about convergence and divergence.
Hocam,
Buyurun.
epsilon 2'yi nasıl belirlediniz az önce?
It should be valid for all epsilons, okay? So it's given any epsilon, you should be able to find the n value. Okay. So I just picked a random one, not a random one, so I just saw that that's not going to be satisfied anyhow. You can say also 1 over 4, 1 over 8. So if a sequence is converging, you can shrink that epsilon as much as you want. You should be still find the n value where all the vectors fall in that radius. You can shrink this radius of the ball as much as you want. You should still be able to find the n value for integers greater than that. The vectors all fall within that radius. Okay, so we failed to do even with at a very early stage. So when I picked epsilon is equal to 1/2, I couldn't find any n value, and I concluded that the sequence is not convergent to 0.
Hocam bir şey sorabilir miyim?
Yes, please.
Bir sequence'ın convergent mı değil mi olması değil de bir sayıya hani convergent olmasından
Exactly.
falan bahsediyoruz değil mi?
Exactly. At this stage, we show that if this sequence is convergent to 0, okay? So that's what we have shown so far.
Bir önceki soruda da öyle yapmıştık.
Exactly. And later we will come to that because of the fact that the next definition will save us from that definition, that the converging value. In many cases, it might be difficult to find that limit value. So there's another form of definitions which is similar to convergence, but not exactly. And that definition comes as the Cauchy sequence. So I will talk about that right now. So once again, in most engineering applications, we are interested in the convergence of the algorithms. And the problem is that we don't know the limiting value for the convergence, okay? So, but the above convergence definition, as your friend just mentioned, depends on the converging value, right? The limiting value of the limit of the series. So for that thing, there is another definition where we don't require, we still think about some series convergent in some sense, okay, in one sense, but without using the limit value definition, okay. So instead of looking at the distance of all the elements in that sequence to the limiting value v bar, we will look at the distance between the elements of the sequence. So let me show that. Okay, so again, the next definition is the definition of a Cauchy sequence, and it's defined on normed vector spaces with V, F, and proper norm definitions. And the sequence Vn in that vector space is said to be Cauchy if for all epsilon you can find an n, which is well defined on epsilon, such that the norm between the two elements with Vn and Vm is less than or epsilon for all n and m greater than n. Okay, so in the previous one we were saying that we were checking the distance between Vn and V bar, and that should go to 0 as n goes to 0. Here we are checking another condition. We are checking the distance between the two elements of the sequence, and as n and m goes to infinity, that distance should go to 0 for any sequence to be Cauchy. Okay, so here is one remark that we will prove, that every convergent sequence is a Cauchy sequence, but the converse in general is not true. Okay, so we will say that every convergent sequence is a Cauchy sequence, okay? So we'll try to prove that. Let's start. So. Okay, so suppose there's a sequence which is convergent. So let's start from that. So suppose the sequence Vn from 1 to infinity is convergent. Yes, convergent to a limiting value V bar, okay? And that is in our vector space. Then we will investigate the difference between Vn and Vm as n and m goes to infinity. Okay, so let's try to write down the norm of Vn minus Vm. Okay, so to that expression, I can add and subtract V bar over here. So I will have such a thing like Vn minus V bar plus V bar minus Vm over here. And by doing so, I was able to get an expression similar to the convergence definition, the difference of the elements to the limiting value over here, right? And I would like to show the sum of those differences less than a value. So which property I should use? The triangle inequality for the norm definition, right? So according to the triangle inequality, that thing is less than norm of Vn minus V bar plus norm of V bar minus Vn. Okay. And since Vn sequence is convergent, as n and m goes to infinity, that sum will go to 0. Okay, so and this is equal to norm of Vn minus V bar plus norm of Vn minus V bar, and as n goes to infinity and m goes to infinity, that sum goes to 0. Okay. So we simply said that so the norm of that difference is already greater than or equal to 0. So let me write that. Norm of Vn minus Vn is always greater than or equal to 0. We also show that it is less than or equal to 0 as m goes to infinity. Then we can conclude that norm Vn minus Vn goes to 0 as n and m goes to infinity. So basically the idea is that for a convergent sequence, all of the elements in the sequence should get closer to the limit value of the sequence, right? And if they are getting closer to the limit value, they will also get close to each other as well. Okay. Therefore, as n and m goes to infinity, as those sequences are getting closer to their limiting value, the difference between the elements of the sequence is also getting smaller. So that is the basic idea of that proof. All right, so we will consider now two examples to give the definition of completeness in norm spaces. So consider the norm space of rational numbers. And again, the field is defined as rational numbers, and the norm is defined as being the absolute value. Okay. And the question is the sequence 1 plus 1 over I factorial I from 1 to n, and it's going from 1 to infinity, convergent? So that expression here as n goes to infinity is converging to the e value, okay, is equal to 2.71828, etc. Okay. So these sequences getting closer and closer to a value, right? But the problem is that the sequence is not convergent, because the problem is that the limiting value, e value, is not in our vector space. So remember that if we go, let me write down, first of all, e is an irrational number, right? So e is not in our vector space Q. And to have a sequence to be convergent, we need a limiting value in the definition of the convergence, right? So we need to have the limit v bar in our vector space, okay? But in this example, the limit v bar is not in our vector space. Therefore, this sequence is not convergent, okay? Therefore, this sequence is not convergent. Okay. And the next definition is about the completeness of the norm spaces. So a norm space is said to be complete if every Cauchy sequence is convergent. Okay. And a complete norm space is called a Banach space. Okay. Later, we will also see something called Hilbert spaces as well, which will be related. Okay, now we have another example, and I will give one example of a normed space that is not complete, okay? So let's have a look at the definitions over here and try to make some sense. All right, so let V be the functions f, which are taking values between -1 and 1, and they're taking real values. F is continuous, okay, so that's important, and the absolute value of the integral of the absolute value of f of t in this interval is bounded, okay. And it says that, okay, let us define the norm of f as the absolute value of the integral of its absolute value in that interval. And let us consider the sequences fn as follows. So I will start by plotting f1. So let me plot these things first. And then I will plot the function. I will first plot the axis, not to change the colors twice. Okay, so f1 is something like this. So this is 1. And that is equal to 1. Okay, so this is f1. This is -1. And f2 is something like this. This is 1/2. And f3 is this is 1/3. So basically fn is something like this. This is 1/n. So first question is the sequence Cauchy? Okay. Is the sequence Cauchy? So we know to check if that sequence is Cauchy, we need to consider the definition of Cauchy, right? So we need to consider the norm of fn minus fm and see what happens there as m goes to infinity. So norm of fn minus f of m. Okay, and that is simply equal to integral from -1 to 1 absolute value of fn of t minus f of t dt. Okay. And if we plot that thing, so it will be something like, so let's write fn and fm, it will be something like that. So I will first plot the axis. Oh, if I can. Okay, suppose this is fn, okay, and this is fn. And let me pick another color, and I will plot the fm. And suppose this is fm. And the integral of the difference of these functions in absolute value is that area, right? So that is the area that we will be talking about. So I'm just let me back here. This is the area. Let me see. A over there. Okay. And then that area is simply equal to 1 over 2 times absolute value of 1 over n minus 1 over m. And what I can show is that as n and m goes to infinity, that area is going to shrink down to 0, right? So for n of m greater than n, that value will be for sure less than or equal to 1 over 2 of absolute value of 1 over n. Even in the worst case, one of them goes to 0, the other one stays there, and that will be less than 1 over n. So,
Hocam
buyurun.
burada fonksiyonda şu y ekseninde kestiği nokta kaç? 1 mi?
Evet. So, by doing so, we can say that as m goes to infinity, the norm of fn minus m goes to 0. So, as m goes to infinity, norm of fn minus fn goes to 0. And as I said before, so if you are given an epsilon, you can limit that norm as 1 over 2 of n and find your n value accordingly. So I can conclude that the sequence is Cauchy. Sequence is Cauchy. Okay, the second question is the sequence convergent? Is the sequence convergent? Okay, so for that thing, we should first ask, so where does the limiting function go to, right? So what is the limiting function? So if I plot fn as, sorry. Okay. So limits as n goes to infinity fn, that will be, as you see over here, this was f3. Fn will be something like this, right? So that is n and that goes to infinity. So let this be the f bar, the limiting value. So all of these sequences are getting closer to and closer to this f bar function over here. But the sequence is not convergent. And do you see why is that? So let me write it down that it is not convergent. Can you tell me why? Every sequence is getting closer to this, every element in the sequence as n goes to infinity, getting closer to that f bar value. But the problem is that that f bar value is not in our vector space, right? Because we said that our vector space defined on the continuous functions. But the limit value f bar here is discontinuous at 0, right? So since the limiting value is not in our vector space, the sequence is not convergent. Okay. Then is this vector space complete? So for this vector space to be complete, every single Cauchy sequence must be convergent, but we found one Cauchy sequence that is not convergent. So therefore, that space is not a complete space. Okay. V is not. Do you have any questions? So as
Hocam
buyurun.
ben sadece şu hani limiting case diyoruz ya. O şey mi demek yani
Neresi limiting case demişiz?
ya burada da dedik mesela F bar diye ya da 23. sayfada da mesela ilk convergence'ı tanımlarken yine V bar eleman V olacak falan gibi.
Exactly. So this is f bar is so I start from plotting f1, f2, f3, and fn is going to look like this, right? As n goes to infinity, I said this is f bar.
Yani limit demek n dediğimizin son infinite
Exactly.
gitmesi değil mi?
And we are looking for that the limiting value of those things. Let me show you over there, v bar over here. And as n goes to infinity, we want that distance to be less than epsilon. That's what we want. Okay. So in this case, we find these all elements in the sequence as n goes to infinity are getting closer to and closer to that f bar over here. But another condition is that f bar value should be in our vector space. If that f bar value is not in our vector space, then the sequence is not convergent. So what do they converge at the end is outside our vector space. Therefore, the vector space is not complete. Just like the example over here, right? So here, as n goes to infinity, we are getting to a number, but that number is a irrational number. And we start from the vector space of rational numbers, so the limit is not there, therefore it is not also complete. Okay. So that is the concepts of convergence and Cauchy sequences. Any other questions? All right, so in our next lecture, we will continue with the inner products. So let's have a look at that. So I uploaded the lecture notes for that, if I can open. We will next continue with the definitions of inner products, and that will add another dimension in our geometry definitions in our vector spaces, because now we will, with the norm definition, we managed to have a distance concept in our vector space. With the inner product definition, we will get an angle notion in our vector space. And once we have the notion of an angle with the inner product definition, we will define orthogonality, which is a very important concept in linear algebra and linear systems theory, so that we will exploit these orthogonality concepts later for the projection theorem and coming up with minimum norm solutions, etc. So this inner product definition will be as important as the norm definition. We'll see. Do you have any questions?
Hocam ben şeyi anlamamıştım ya 24. sayfada remark'ı. Şey mi bitirdik mi dersi? Devam edecek miyiz?
I think we can answer the question, so we can start in product spaces the next time. Okay. Please do ask your questions. Let's try to see that.
Hocam 24. sayfada remark'ı ispatladık ya.
Alright.
Orada şu en sonsuza giderken M sonsuza giderken satırı var ya oradan sonra çok anlayamadım.
Burada dedik ki so as n and m goes to infinity, the first I'm looking at the sum of two non-negative terms, right? Huh?
Evet.
So I'm looking at this expression, and that expression is sum of two non-negative terms. And I see that those two non-negative terms are going to zero as n and m goes to infinity. Right? The first non-negative term goes to zero. The second non-negative term goes to zero. Okay, so their sum goes to zero, right? And notice that their sum was our upper bound for difference of Vn minus Vm, right? So the norm of Vn minus Vm is always greater than or equal to zero. That's the definition of the norm. We also show that as n and m goes to infinity, they are less than or equal to zero. And we basically show that as n and m goes to infinity, that difference goes to zero. Is that any clear now?
Teşekkür ederim hocam.
Perfect. Any other question?
Hocam ben de bir şey soracaktım ama
Buyurun lütfen.
en son çözdüğümüz example'da convergence konusunda yorum yaparken f'in continuous olması gerekiyor diye bir ifade vardı soruda.
Evet, that was the vector space definition. Yes.
Evet. Eğer o definition'da olmasaydı bizim ikinci part için
Exactly.
yapacağımız bir yorum nasıl değişirdi?
Then if this wasn't limited with the continuous functions, then we were saying that we could only say that Cauchy sequence is convergent, okay? So we found a counter example for the not being a complete vector space, right? So we found a counter example, but we were done. But if this wasn't limited with the continuous functions, okay, all real valued functions, then that limiting series was going to be also convergent, but it's not going to be conclusive for us only with one example, because we will check all Cauchy sequences must be convergent. So we just checked one of them.
Yani complete olması konusunda da bir yorum yapamazdık bu durumda değil mi zaten?
Onun için ayrıca ispatlamamız lazım. Yani tüm Cauchy sequence'lar için bu geçerlidir diye bir ispat yapmamız lazım.
Teşekkür ederim hocam.
Very good question. Any other questions? All right, so if not, we will continue on Friday, and so we will have our quiz next Friday, and we will have our lecture this Friday. And after the lecture on Friday, you can also come to the department to EA building, so that we can meet and greet. And if you would like to chat and talk about the course or some other things, we can meet there. Probably in a classroom which might be EA 209 or 207. I need to check the availability of those classrooms, but I will send the announcement for that from OTTI class, so you will be knowing the place.